Connaissance. Recherche.
Sciences.
Des sciences mathématiques.
Théorie.
Physique.
Philosophie.
Conférence.
Archéologie.
Environnement.
Nature.
Merci bien, Edouard. Mesdames et messieurs, chers collègues et amis de la recherche polaire et de la science du climat, je suis très heureux et honoré maintenant aussi d'être invité à cette réunion importante sur la clôture de l'année internationale polaire. Comme vous verrez, il y a beaucoup de résultats très importants pour la recherche du climat et pour aussi comprendre la sensibilité du système de notre planète à la perturbation humaine. Mais je voudrais, avec votre permission, continuer mon allocution en anglais. C'est plus facile pour moi, évidemment. Merci. So, I would like to take a few minutes to tell you about the importance of polar research for the understanding of the climate system. The climate system which is perturbed and changed by the activity of man, as you have already heard from Claude Lorius and Edouard Bard, and which has been evident since many years. The pioneers have alerted us to ongoing changes already in the 50s, and in fact it was the International Geophysical Year and the Third International Polar Year, which was the opportunity to take base measurements in various locations of the planet, which today, as you will see, serve as a baseline to put into context the measurements and observations that we have gathered in the last few decades and which are making the point in a very evident way that humans have changed the climate. Now, in the last IPCC report, which was published in February 2007, in fact, in this city, we have passed the first part of this report in a memorable meeting. This very sentence has been accepted by the plenary of IPCC in an astonishingly short amount of time. Very little discussion was held. In fact, if I remember correctly, the discussion revolved about the question how to translate the word unequivocal into French. And there was a little debate. A few countries have raised their concerns. And in the end, thanks to the French delegate, the French delegate raised a hand and resolved the situation by saying, this is very simple for us. Ça veut dire pas équivoque. And here it stands. Warming in the climate system is unequivocal. There is no doubt that the planet has warmed. We can quantify it. But there are other statements which are very relevant when it comes to polar research. And here is another statement in the summary for policymakers, which says it is likely that there has been significant anthropogenic warming over the past 50 years, averaged over each continent except Antarctica. That was the state of knowledge around 2006, 2007, and that was, with all honesty, what we could say from the scientific point of view about the changes in the climate system. Now, a few months later, people have actually scrutinized the observations over Antarctica from many stations. And it's really very telling if you look where this time series starts. It's in 1957. And that is, in fact, the year, the International Geophysical Year and the third International Polar Year. And you can see now the significance, really, of such events for the science and for the understanding of the planet, which is our home. You see very clearly now, in a publication published earlier this year, the warming has finally arrived also in Antarctica. We can measure it, it's visible, but it's a great challenge to see it. As you see here in these curves, the temperature in Antarctica shows large fluctuations, so-called natural variability, which often disguises the long-term trends. But now they are also realized and detected in both parts of Antarctica. A very significant result. Let me give you a small overview of the few topics I would like to touch upon today. I will show you a few new items and pieces of knowledge from polar ice cores. I will then talk about surprises in the Earth system. I will turn to Arctic sea ice. I will talk very briefly about ice sheet instabilities and close with a few open issues which I hope the scientific community will be able to resolve or at least make significant progress upon them in the coming 4 to 5 years, in which our duty is to write the next assessment report of the Intergovernmental Panel on Climate Change. Now, one important statement that could not have been made without the help of polar research, in particular without ice cores from Greenland and Antarctica, is the statement that levels of anthropogenic greenhouse gases like carbon dioxide, methane, and other gases have acquired levels that are higher than for many, many years before. This graph shows you that not only the levels are higher, but also the rates of increase are significantly higher. In particular for carbon dioxide, we can now find that the increase over the last 200 years is more than 200 times faster than any increase of carbon dioxide in the natural, unperturbed climate system over the last 10,000 or 20,000 years. Here is now the long-term perspective of two of the most important gases. And it's thanks to a very close collaboration we have enjoyed with the laboratory in Grenoble and the laboratory in Paris here that has enabled the scientific community to actually draw these curves. That is, in blue, the concentration of carbon dioxide in the atmosphere over the last 800,000 years. You see, CO2 was never really constant. It always varied. Natural variability, changes between atmosphere, ocean, and biosphere. But these changes evolved in very clear ranges, between 172 and about 300 ppm. ppm is the measure of number of molecules of carbon dioxide in 1 million molecules of air. Today, carbon dioxide is at a concentration of 386 ppm. And the graph here would not even permit me to show you that concentration. In red, you see the estimate of the temperature, which was measured or derived on the isotopes, the stable isotopes of the ice. Many of these measurements were performed in very high resolution at LSCE in Paris. And in the green curve, you see the concentration of methane, which was primarily measured at the laboratory in Grenoble, LGGE. You see All these parameters show natural variability, the sequence of ice ages, but they also inform us about the unique concentrations that man has now inflicted on the atmosphere in these two gases. The polar ice cores also informed us about surprises in the climate system. You see here an isotopic temperature series or time series from Northrop, which was published a couple of years ago, which covers the last ice age and goes back 123,000 years. The focus should be laid on the variations of temperature that were reconstructed in Greenland during the last ice age. And you see a series of very abrupt warming and coolings. They are all numbered, and they now are referred to in the scientific community as the so-called Dansgaard-Oeschger events, named after two dear friends and pioneers who have started both in Denmark and in Switzerland important areas in polar research. This curve really informs us that the climate system is sensitive and can change very rapidly. And we need to ask ourselves what the significance of this information for today's climate is. In fact, it was the Greenland ice cores that provided the key evidence that surprises in the climate system actually could happen. And a very recent publication tells us, through the analysis of very high-resolution isotopic measurements, which you see here spanning over just 4,000 years, that in many instances, temperature and other atmospheric variables can change within just a few years. This then has led to a strong research program in many areas of the world in which scientists have asked the question, well, if we see very large temperature changes in Greenland, may there be other areas on the planet where we see abrupt change or where we could actually experience surprises? You see here a map of the planet which summarizes the areas. For example, the red area, that's the Eastern Tropical Pacific, in which Edouard has shown you the very particular response of the temperature just in the year 2007. But one question that scientists would like to answer is how this very important system of natural climate variability will evolve in the next 100 years. As is very known, this El Niño Southern Oscillation phenomenon is responsible to a large extent for the economic well-being of the South American countries when it comes to fisheries and resources. So we want to know how this system will evolve, whether frequencies change, whether amplitudes change, or whether perhaps the system moves into a totally different equilibrium where you might have a permanent condition of El Niño or La Niña. On the continents, you also recognize some hotspots. For example, in Siberia, I will come to that also at the end of my talk, permafrost. The question, what happens to the permafrost when the warming will continue? And many other areas are now in the focus of the research community. One in particular, also mentioned by Edouard Bard, is the question how ocean circulation will change in the future. In particular, the northward extension of the Gulf Stream, which is responsible to a large extent for the benign climate in Europe. You see here a very messy and busy figure with many curves. This just is an illustration that the science is not yet at the stage where we can make educated and good information to the public. We simply don't know how the system will really develop. The only thing we could say is that most of the models show a reduction of that circulation, but we also don't see any abrupt surprises in that particular variable. But we should be very alert and see what the science will produce in the next 5 years, and hopefully we will be in a better position then with more sophisticated, better climate models, more observations available to calibrate these models to inform the public in a much better way with fewer uncertainties. Let me turn to Arctic sea ice, a very vulnerable part and important ecosystem component in our climate system. We all remember the record year 2007. Edouard Bard showed you the global situation of temperature anomaly. I now focus in on the polar area of the northern hemisphere, and you see the sea ice extent in white as it was observed in September 2007. In comparison, the purple line shows you the average ice margin in the years 1979 to 2000. And it's very evident that this was a record minimum year of summer sea ice extent. The question, obviously, is whether we have already passed a tipping point, whether this is already the new situation that we have to live with in the Arctic, an Arctic that is essentially ice-free. The question is still open, but what is clearly evident is the fact that the planet has evolved in a more rapid way than any of the climate models whose results you see here in the fine lines in the background has predicted. These climate models also show a reduction in Arctic sea ice, but the observed one given in the red curve tops all these reductions. It shows a steeper descent of this Arctic sea ice. And nature itself tops this again with the Arctic sea ice extent in 2007, almost a step down from the long-term trend observed since the 50s. Now, this is a simulation of climate models that actually do show very abrupt changes to be expected in the sea ice extent, but only around the year 2030. So the fact that we've seen it already in 2007 is actually quite alarming. Now, the year 2008 is also given here as a reference. The Arctic sea ice reduction was not as severe as in the year 2007, but still we are very much and significantly below the simulations of the climate models. That is why it's so important to be persistent in observing the climate system, not only to simulate and use the best and most sophisticated models, but actually going there into the polar areas, into the Arctic, to the Antarctic, and persistently provide high-quality measurements over large scales. Let me now come to the point of ice sheet instabilities. You may remember this diagram that was published in the fourth assessment report of the Intergovernmental Panel on Climate Change, which informs the public about the sea level rise that results from 6 different carbon dioxide emission scenarios. The science is very sophisticated. We are able to distinguish the amount of sea level rise due to the thermal expansion of the ocean, due to the melting of the Antarctic and Greenland ice sheet, and due to the melting of the land glaciers. But there is a large uncertainty that we had to report at the time. We had to say that up to 20 centimeters of sea level rise in the next 70 to 90 years, we could not be sure about. And I've indicated this with these blue bars. The reason for this uncertainty is associated with ice sheet instabilities, the possibility that Greenland and Antarctica actually might melt faster than we anticipate, might lose ice through ice dynamical feedbacks with the ground, and interactions which are poorly known, so as to increase sea level much more than is due to the better understood physical processes. Now, the science even goes a step further that talks about tipping points or points of no return. In other words, critical warmings in the climate system, both globally and locally over Greenland, on the order of 2 to 4 degrees Celsius, completely feasible within the next 100 years, which then would result in an irreversible meltdown of Greenland. Now, the science is still out there. Many groups are questioning their computers, feeding them with new ice sheet models, taking into account the latest known processes to really be sure about the accuracy of the predictions. But this is a real possibility we should not forget. Now, science has also informed us that these instability processes have different origins, both in Greenland and in the two very different parts of Antarctica, Western Antarctica and Eastern Antarctica. And they are due to a range of processes from basal melt due to elevated geothermal heat, to specific shapes of the bed topography, which induces instabilities in the ice flow, to actually lake formation, which is well known at the underside of the East Antarctic ice sheet. Now, the present-day observations should be alarming as well. If you look at the surface mass balance of Greenland, which is shown on the right-hand side, you see in the reddish and yellow colors all those areas where accumulation is recorded. That is, the ice sheet is actually gaining mass from accumulation in the interior. But at the same time, it's losing mass at the outside, at the fringes of the ice sheet, where you see the blue colors. In fact, that melting actually overwhelms the accumulation in the interior, which leads to a slow reduction of the overall mass of Greenland, and in consequence, to an accelerated sea level rise. Let me now come to the conclusion of my short overview. It's clear that each of these polar years and dedicated geophysical years has provided a quantum leap in our understanding of the Earth system. So they are not merely celebrations of a particular area of research, but they release sufficient funding and they accelerate the motivation and the energy of the scientists to actually dedicate a sufficient and substantial amount of their time to a focused topic. As this was the case in 1957, where you remember the Antarctic Temperature Time series have started, and in the last polar year, which enabled us to embark and bear fruits of the latest ice coring projects. All these many projects have increased our knowledge. I think it's clear by now that the polar areas are very sensitive recorders and indicators of past and future climate change. But at the same time, because they are so sensitively reacting to climate change, as we see evidence for it in the polar ice cores, they are also particularly vulnerable. And therefore, we need to pay particular attention to the polar areas. I would also like to remind that essential new observations and paleoclimatic reconstructions from polar areas permit a more reliable quantification of natural ranges of climate change. The last 50 years, during which we have essentially observations from the polar areas, are just a tiny, tiny window of the rich dynamics that is embedded in these archives, in the ocean, on land, and on ice. And finally, I think one of the very grand open questions resides with the question how the ice sheets both in Greenland and in Antarctica, will react to the ongoing global warming. Better understanding is needed in order to reduce the uncertainties in long-term sea level projections. Let me close with a few key questions that, in my view, need to be answered, and perhaps we can hope that in the next assessment report we're actually able to contribute to an answer of these questions. The West Antarctic ice sheet has come into focus again. There were years in the 70s and 80s where scientists hypothesized that this ice sheet actually could be unstable. Then a few years or decades where this apparently was to no interest of that generation of scientists, and that has resurfaced again. The question, how will this ice sheet react to both temperature, ocean warming, and sea level rise? Models have indicated that perhaps there could be tipping points associated with Greenland. Obviously, we want to know better whether this is true, and if it is true, we would like to know where these tipping points are. Another issue is associated with permafrost. It's clear that through the polar amplification, these areas will warm rapidly. The warming may release clathrates and gases that are trapped today in these vast areas and wetlands that will become permeable to such gases. And the question is whether such release of gases will contribute to the gases that come from anthropogenic activity. One topic I think that should not be forgotten when we talk about global warming is in fact quite an unfortunate number because it focuses your attention to only temperature. But climate research has really demonstrated to us that with the temperature, many other parameters will change. The hydrological cycle will change. I'm convinced that this will be the fiercest and strongest change with the greatest challenges ahead of us. But also the chemical status of the ocean will change through a direct effect of increased carbon dioxide concentrations in the atmosphere, which will decrease the pH in the ocean, and that will have an effect on marine ecosystem, which is not yet fully quantified. And clearly, the overarching question, if we look back to the past, we see traces of irreversible natural changes when you go from an ice age to a warm phase and vice versa. The question, therefore, that is before us, will man actually irreversibly change climate, even if we mitigate, even if we reduce the emissions of carbon dioxide? It's clear already now that some parts of the climate system will change in an irreversible way, to which we have, as humanity, adapt ourselves. Thank you very much.